Okay, this is the mechanical waves unit. The big idea for this unit is big idea number 6. Waves can transfer energy and momentum from one location to another without the permanent transfer of mass, and also waves serve as a mathematical model for the description of other phenomena, specifically atoms and electrons and things like that. Okay, so for this unit, the learning goals, I want you to be able to correctly classify a wave, explain the difference between mechanical and non-mechanical waves. I want you to understand how amplitude is related to energy, and calculate things like wave speed, wavelength, period, and frequency. All right, so getting started here. A mechanical wave is a disturbance in a medium. So, going back to your childhood, think about when you throw like a pebble or something into a pond. It makes these ripples. Those ripples are waves. Now, as those waves travel out away from that initial strike, I want you to realize that the waves are moving, but the material or the medium is not. Um, we can think of the water as just kind of like moving up and down, but it's not moving side to side. It's not like we can take water molecules where the pebble first hits the water, and those very same molecules will travel all the way back to the other side of the pond. It doesn't work that way. So what a wave is something that's oscillating, and we just got done talking about simple harmonic motion. So waves can propagate via different oscillatory motion, and there's two types, transverse and longitudinal. So in a transverse wave, the particles will be moving perpendicular to the direction of the wave's motion. So I have an example of that right here. It kind of looks like the sine graph, where we have our sloping up and down. There's some important things to notice. We've got our wavelength. Now, I like to use a lambda symbol for wavelength. We have our amplitudes. So from here, that'd be like a positive amplitude. Then here to here would be like a negative amplitude. As this is moving, let's say this wave is moving past this point right here. So as this wave moves past this point, the amount of time it takes for one wavelength to pass this point would be the period. All right, so some examples. Water waves. Waves on a string. You think about a guitar string or something like that. Electromagnetic waves. Electromagnetic waves include things like radar, visible light, stuff like that. And certain types of earthquakes. We'll talk about the different types of earthquakes later, but there are certain types of earthquake waves that they're transverse. All right, the next type is longitudinal. Sometimes you'll hear me call these compression waves. And with these, the particle motion will be perpendicular, or I'm sorry, particle motion will be parallel to the direction of the wave's motion. So with these, um, a slinky is really the best example for longitudinal waves. So as this wave travels through the slinky, we get this part where um, the rings of the slinky are pushed together or compressed. And we have this part where they are stretched apart. We call that rarefaction. And as this moves through the medium, um, the parts, so it would compress and then stretch apart, compress, stretch apart, compress, stretch apart. And that's how the wave moves through this. Now we can still use a transverse wave as a way of showing this. So if I were to make a quick little sketch here, what I could do is I can use positive amplitude for the compression, negative amplitude for the rarefaction, and I need to draw this a little better. Let's see here. There we go. So we can still have a wavelength, we can still have an amplitude, all that other fun stuff, period, wave speed, um, but longitudinal waves, they use compressions and rarefactions. So for this, some examples include sound. Sound is a compression wave. Obviously, the slinky. And again, certain types of earthquakes. Now, as waves move, um, for mechanical waves, they require a medium. A medium is something for the wave to move through. As the wave travels, the medium is what does the waving. So if you think about water, as a wave travels through water, water is the medium, water does the waving. Electromagnetic waves are special. They do not require a physical medium. So here I have a chart of some examples here. We got mechanical waves and electromagnetic. Sometimes these electromagnetic are just called non-mechanical. And some examples of mechanical waves. We got our longitudinal and our transverse. So we got our examples, sound and water. And then the electromagnetic, which do not require a medium. We have visible light, microwave, infrared, X-ray, ultraviolet, radio waves. There's also gamma. Oh, is included there as well. It's kind of fun to say this, but in space, no one can hear you scream. And the reason for that is because sound is a mechanical wave. It needs a medium to travel through. Now, most people think that sound only travels through air, and that's actually false. Sound can travel through liquids and solids as well. And in fact, sound is faster traveling through liquids and solids than it is through air. A fun experiment for this is this summer when you're in a swimming pool, dive underwater, have a friend make a loud sound. And the moment you hear that sound, stand up out of the water, and you should hear it a second time, because sound will travel faster through the water and slower through the air. All right. The next thing I want to bring up is the different parts of a wave. We've kind of touched upon this. We got wavelength, we got crests, troughs, amplitudes, and all that other fun stuff. And I'm sure a lot of this should look familiar to you. Amplitude is the maximum displacement of the wave from its equilibrium. And we've talked a little bit about how to find amplitude before. This model here should look very familiar to you. That's our way of calculating what the amplitude is at a certain moment in time. Classically, the energy carried by a wave depends upon and increases with amplitude. So, as it turns out, the energy that a wave carries is proportional to its amplitude squared. So, in other words, if I triple the amplitude, the wave should carry 9 times more energy. Or, if I wish to have a wave carrying, I don't know, 25 times more energy, the amplitude needs to be 5 times larger. Um, so for periodic waves, the period is the repeat time of the wave. So basically, the amount of time it takes for one complete wavelength to pass a point, that would be period. Frequency is how many repetitions or how many oscillations per second. Period is measured in seconds. Frequency is measured in hertz, where hertz is an inverse second, or a 1 per second. For the periodic wave, wavelength is the the repeat distance, or a complete oscillation. Now for some math um, for our periodic wave. First off, we have the frequency is equal to 1 divided by the period, and the period is equal to 1 divided by the frequency. Now velocity, if we have constant velocity, it's delta x over delta t. As it turns out, waves are pretty close to constant velocity. So for the speed of a wave, our delta x is going to be the wavelength, lambda, and the time is going to be the period, t. Substituting in, we can also see that v equals wavelength times frequency. So take a look at that, and you should be able to follow that math in your head pretty quickly. Now, these two formulas are always true. A very special case, if we're looking at the speed of waves on a string. This is the model for the speed of waves on a string. Now notice that's a string. That will not work for sound, it will not work for water waves, but just for a string. And this T is the tension. Yeah, it's a force. And mu, it's not the coefficient of friction anymore. This one is the linear density. Which is mass divided by length. All right, this concludes the first video.